Today I want to discuss in detail what it takes for an object to be in complete static equilibrium. For an object to be in static equilibrium, it is not enough that the sum of all forces is zero. But what is also required, that the sum of all torques relative to any point that you choose is also zero. And that will be the topic today. If this is an object free in space, and let's say the center of mass is here, and I have a force on this object in this direction, and another force on this object in opposite direction, but equal in magnitude, then the sum of all forces is zero. But you better believe it that there is no equilibrium. There is a torque. And if this distance equals b, then the torque on that object relative to any point that you choose, doesn't matter which one you take, the magnitude of that will be b times f. And if there's a torque, there's going to be an angular acceleration. Torque is I alpha. And so it's going to rotate. In this case, it will rotate about the center of mass. So it's not static equilibrium. The torque, in this case, would be out of the blackboard. So it's going to rotate like this. So we've got to keep a close eye on torques as much as we have to on the forces themselves. So today I have chosen a letter as my subject of static equilibrium. I put a letter against a wall. Here's a wall, and this is the letter. At point P, where the wall is, there is almost, let's say there is no friction. Mu of P is zero. At point Q here, where it's resting on the floor, there is friction. The static friction at point Q, we'll simply call that mu. The letter has a mass m, and it has a length L. So here is the center of mass of that letter, right in the middle. And this angle equals alpha. We know from experience that if this angle is too small, that the letter will slide. And so I want to make the topic today, what should that angle be so that it does not slide? Well, we have here a force, mg. That's gravity. Then we have a normal force here. I call that nq. We have friction in this direction, because clearly the ladder wants to slide like this, so the frictional force will try to prevent that, will be in this direction. At point P there is no friction, so there can only be a normal force, and I call that N of P. So these are the only forces that act on this object. And now we can start our exercise, and we can say, all right, the sum of all forces in the x direction have to be zero. So that means that N of P must be in magnitude the same as the frictional force. Now the sum of all forces in the y direction have to be zero. So that means that mg must be N of Q. N of Q must be mg. But now we need that the sum of all torques have to be zero. It doesn't matter which point you choose. You can pick any point. You can pick a point here or here or there or there. You can pick C, you can pick P. I choose Q. The reason why I choose Q is because then I lose both this force and that force. And I only have to deal with this one and that one. And so I'm going to take the torque relative to point Q. So we have NP, we have the cross product of the position vector to this point times the force. Since the length is L and the angle is alpha, this is L sine alpha, so I'm going to get NP times L sine alpha. And I call a torque that is in the blackboard, I call that my positive direction, and a torque that is out of the blackboard, I give that a negative direction. So this one is in the blackboard, so I call that positive. The next one, mg, is going to be a negative torque. And so now I need the cross product between the position vector and mg. So that is the length here, which is 1/2 L cosine alpha times mg. mg, 1/2 L cosine alpha, and that now must be 0. So I find then that N of P, that is the normal force at point P, I lose my L, equals M divided by 2 times the cotangent of alpha, and that must be the frictional force. So I know what the frictional force is, given by this result. Now, I don't want this ladder to slide. So now I have a requirement that the frictional force must be less or equal to the maximum frictional force possible. And the maximum frictional force at this point Q is mu times the normal force. So my requirement now is that N over 2 times the cotangent of alpha must be less or equal to mg times mu. Mu times mg. Did I lose a g here? Yes, I did. I have here a g, and I have here a g. Correct? Because if I have this force here and this position vector, then I have mg. So there is a g here. And so there is a g here. And so I lose my mg, and so you find that the cotangent of alpha is smaller or equal than 2 mu, or the tangent of alpha is larger or equal than 1 over 2 mu. And so that is the condition for the ladder to be stable. And when you look at this result, it tells you that the larger mu is, the smaller that angle. And that's very pleasing. That's exactly what you expect. And if mu is very low, then the situation is very unstable. Then it will slide almost at any angle. If we take some numerical examples, for instance, I take mu equals 0.5, then alpha would be 45 degrees. And if the angle is any less, then it will slide. If you take mu is 0.25, then the critical angle where it will start to slide, I think, is somewhere near 63 degrees. But you can check that for yourself. So the angle has to be larger than that number for the ladder to be stable. This result is very intuitive, namely that if the angle is too small, that the ladder starts to slide. I have a ladder here against this wall. We have tried to make this here as smooth as we possibly can. It's not perfect. So it's only a poor man's version of what I discussed there. But in any case, the friction coefficient with the floor is substantially larger than the friction coefficient here. And what is no surprise to you, that if the angle alpha is too small, then there's no equilibrium. The angle of alpha has to be larger than a certain value, as you see there. And then it's stable. That's all I want you to see now. But now, we're going to make the situation more interesting. And in a way, I'd like to test your intuition. Suppose I set the angle of the ladder exactly at the critical point. In other words, I'm going to set it so that the cotangent of alpha is exactly 2 mu. So it is hanging in there on its thumbs, just about to start sliding. And now I'm going to ask one of you to walk up that ladder. To start here, and slowly walk up that ladder. Do you think that stepping on that ladder, starting off, is super dangerous, that the ladder immediately will start to slide? Or do you think that actually your being at the bottom will make it more stable? Who thinks that it will immediately start to slide? A few people. Who thinks that it will not start to slide when you step on the lowest? All right. We'll see what happens later on. Now this person is going to climb the ladder, and then there comes a time that it passes point C and reaches point P. Will it now be safe to do that? Or do you think that now it's going to be very dangerous? What do you think? Who thinks that you shouldn't get too high up on the ladder? Who thinks it makes no difference? You can go all the way up to the end. There are always a few very courageous people. Okay, well this is what I'm going to analyze with you. And most of you have the right intuition, but we're going to look at this in a quantitative way as I know how to. So we're going to put a person with mass little m on that ladder, and we put the person here. So this force here is little mg, and let's make this distance d. And now we're going to redo all these calculations. We start completely from scratch. The sum of all forces in the x direction has to be 0. No change. N of P must be F of F. Now the sum of all forces in the y direction has to be 0. Now there is a change. So now we have that N of Q must become larger, must be equal to capital M plus little m times G. So the maximum friction, which is mu times NQ, now becomes mu times m plus m times G. So the maximum friction goes up. Now we need that the torque, and I pick my point Q, relative to point Q, equals 0. Well, the first two terms haven't changed. So I have N of P times L sine alpha minus mg times 1/2 L times the cosine of alpha. But now we have a third term, namely this position vector and this force. And so now we're going to get this distance, which is d cosine alpha times this force. So we have here minus mg times d cosine alpha, and that now equals 0. So I'm going to take N of P out of here. I can take G cosine alpha out. So if I take G cosine alpha out, I have ML divided by 2 left over, plus little md, and then I have to divide by L sine theta. Not theta, but alpha. And so now I can write for cosine alpha divided by sine alpha, I can write cotangent alpha, and I'll bring the L inside here. So I have G cotangent alpha times m over 2 plus little md divided by L. And that now must be the frictional force, because NP is still the frictional force. Let me make sure that I have this right. Yes, I do. G cotangent alpha m over 2 little md over L, that is the frictional force. Notice that the frictional force is going up, because this term is added, and we didn't have that term before. Before we only have this term, which you see here. So your first thought may be that the situation has become more dangerous, because if there is more friction, well, the ladder was set exactly at that critical point. It was hanging on there by its thumbs. So if the friction goes up, you may say, my goodness, it will probably start to slide. However, what you overlook then is that the maximum friction has also gone up. And so we have to evaluate this now in comparison with the maximum friction. And the best way to do this is to think of this first as making d equals 0. So we said the person starts at the bottom of the ladder. And we ask this person to gradually climb up. Now notice, when D equals 0, that the frictional force is exactly the same what it was before. There is no difference. That frictional force has not changed when D equals 0. But what has changed is the maximum friction. The maximum friction has this little m in it. And that's independent of D. There is no D anywhere here. So if the maximum friction goes up, and the friction itself remains the same, clearly the ladder has become more stable. And so you can step on the lowest thread and nothing will happen. On the contrary, the situation will become more stable. As the person starts to move up, the frictional force gradually increases because this term goes up. But the maximum friction remains the same. It's independent of D. And so now there comes a time that this force becomes larger than the maximum friction, and then the ladder will start to slide. And that, of course, is what we want to find out now. So now the situation is only safe as long as the frictional force is smaller or equal to the maximum value possible. And that's the case when G cotangent alpha, but remember we set it at the critical angle so that cotangent alpha is 2 mu. So I can replace this by 2 mu. Because that's the way I set up my experiment. I start that way. I don't start with a random angle. I start exactly at the angle so that the ladder is sort of just hanging in there. So cotangent alpha is 2 mu. M divided by 2 plus M times D divided by L. This now has to be less or equal to this value. Mu times M plus M times G. Notice I lose my G, I lose my mu. I have here 2 times M over 2, which is M, and I have 1 M here, so I lose my capital M. And so I find that 2md over L has to be less or equal to M. I lose my M, and I find that D has to be smaller or equal to L over 2. And that is not unlike most of your intuition. Namely, as long as the person who steps on the ladder stays on this side, the situation will become more stable. Certainly when the person starts here, the stability has enormously increased. As you gradually approach that point here, the center of mass, where D is exactly L over 2, then of course the situation becomes again extremely critical here, but when you're over this point, it's no longer critical, and the ladder will start to slide. So in a nutshell then, we set the ladder at the critical situation. It's about to start sliding. We put a person on here, it becomes more stable. The person walks up slowly, the frictional force will increase because of this term. The maximum friction will not change, has already gone up because the person is on the ladder, and as the person approaches this point, the situation becomes less and less stable all the time. Right at this point, we're back to where we were. Situation is about as critical as it was before the person steps on it, and when the person proceeds, then the ladder will slip. And I can show that to you, at least I can make an attempt. I have here that same ladder, and now what I will do is I will set the angle alpha, not exactly at the critical point, but a little lower, so that when I let it go, we all see that it will slide. So it's past the critical angle. The angle is smaller. But now I have 4 kilograms here. I wasn't going to ask any one of you to walk up this ladder, believe me. And I wasn't going to do it myself either. So you see, it is unstable. And now I put the 4 kilograms on here. And I can let go, and the ladder has become stable. Do I take it off? There it goes. So the person standing very low made it more stable. Exactly consistent with what we just saw. Now I make the angle alpha a little larger than critical. So the ladder is happy. It's happy. But now the person is going to do something dangerous. It's going to walk and stand here. And he shouldn't do that, as you see. That's exactly what you've seen there. So the friction plays an essential role for us to get static equilibrium, and that is often the case.